All right, in 9.3a, we're going to start looking at how do you handle it when you have two means and you're estimating the difference between two means. Hopefully you'll see some similarities of how we handled it with proportions, and because it's very, very similar. Okay, so the first thing we have to do is describe the sampling distribution of x bar 1 minus x bar 2, or the means of our two samples. And the reason we have to do this is in order to use the normal distribution, which gives us probabilities, we have to know that the shape of the distribution is normal. So we have ways to check that out. Okay? So here's the definition. Suppose that x bar 1 is the sample mean in a simple random sample of size n1, drawn from a large population with a mean of mu1 and a standard deviation of sigma 1. And that x bar 2 is the sample mean in a simple random sample size n2, drawn from a large population with mean mu2 and a standard deviation of sigma 2. Then, here's how you know. The shape of the sampling distribution of the difference of the two means, x bar, is approximately normal if, notice you have one. Both population distributions are approximately normal. That means it was given to us, right? Given to us in the problem. Number two, or both sample sizes are large. N1 is greater than 30 or N2 is greater than 30. All right, then the mean of the sampling distribution is simply the difference, okay? X bar 1 minus x bar 2. All right, they're the same. The standard deviation of the sampling distribution of the differences between the two samples is this formula right here. And you'll notice that it's sigma squared over that sample size plus the other sigma squared over that sample size. Add them up, then take the square root, right? So we've learned two conditions that should be met before we construct a confidence interval for population means: random and normal/large sample. Now we're comparing two means. We have to modify these conditions a little bit, all right? So for random, what do you have to do? Well, it says the data have to come from separate random samples from the two populations of interest or form two groups in a randomized experiment. So you have to identify that both of the samples are random or that the experiment is created was random. For large counts, the way we do it with means, remember, is we know that the true distribution of the responses of the two treatments are normal. They tell us that, or both the sample sizes are larger than 30. N1 is greater than 30, N2 is greater than 30. If the population distributions have an unknown shape and the sample sizes are less than 30, then we have to graph the data from each of the samples to show no strong skewness or outliers. And that's pretty tedious if you have to do that because you have to draw two box plots. But we've done this before. We're just potentially having to do it twice. All right, so let's look at this example. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large cups. When the large setting is chosen, the amount of liquid dispensed by the machine is approximately normally distributed with a mean of mu equals 27, standard deviation of 0.8. When the medium setting is chosen, the amount of liquid dispensed is approximately normally distributed with a mu of 17 ounces and a standard deviation of half an ounce. The restaurant manager measures the amount of liquid in each of 20 randomly selected cups filled with the large setting, 25 randomly selected cups filled with the medium setting. Let x bar 1 minus x bar 2 be the difference in the sample mean amount under the two settings. All right, so first question is, what is the shape of the sampling distribution? So what I want you to catch is in the problem, it tells us that when large setting is chosen, the large setting, the amount of liquid dispensed is approximately normally distributed, right? That's for larges. Then it goes on to tell us that when the medium setting is chosen, the amount of liquid dispensed is approximately normal. All right, so because the two populations we're looking at are approximately normal, we know that the sampling distribution of those samples we take will also be approximately normal. Okay, so all we have to do is put that in words. So because we know the two populations are approximately normal, we can assume the sampling distribution of the differences will be approximately normal also. All right? So number 2 says find the mean of the sampling distribution. All you have to do to find the mean is to subtract the two means that are given. So they gave us mu1 was 27, mu2 was 17. These are ounces. So to find the differences, the mean of x bar 1 minus x bar 2 is really just these two things subtracted. 27 minus 17 gives me 10. And that's my mean. That's it. So the third part asks me, okay, calculate the standard deviation of the sampling distribution. Okay, so if you remember earlier, I gave you this formula. It looks like this. Sigma of x bar 1 minus x bar 2 is this big square root. So I take the sigma of the first one, square it, divide it by the sample size. So I just rewrote our data out here. So sigma of the first one squared over 20, because there were 20 cups of large cups tested. And then the medium standard deviation was 0.5 ounces squared over 25. Okay? Then we take the square root. So make sure you do everything on the inside first before you take the square root. When I did that in my calculator, I got 0.205. Okay? And that's how you do standard deviation. So today we're focusing on how to describe the sampling distribution of two means, the difference of two means. And that means you got to be able to explain shape, center, and spread. Okay? Center is mean, spread is standard deviation. All right? Hope this makes some sense, and we'll see you in class.